Assalamu alaikum wa rahmatullahi wa barakatuh. Let's begin the lecture for today. Today we're gonna, of course, Sunday's lecture was the last lecture for the random processes, chapter 6. So if you have any questions about it, we can discuss it. Otherwise, let's begin with chapter 7. مثل ما حكيت بداية السمستر لما حكينا إنه we're gonna cover chapter 7 and 8. We're just going to talk about two topics, يعني just quick introduction about the power spectrum density in chapter 7, and chapter 8 we're going to talk about the response of linear system to random signals. Just two small topics, just so you will know about it, okay? So طبعا chapter الليكتشر تبع chapter 8 آخر lecture كان يحكي عن cross correlation. I'm sure you've seen it on e-learning وما بها شيء straightforward. مثل يعني كأنه يعني نفس الأشياء اللي غطيناها covariance and things like that. ما في شيء جديد. Okay, so I'm gonna assume that you didn't have any questions. If you do, just let me know. Okay. All right. Let's begin with chapter 7. Where we're going to talk quickly and briefly about power spectral density, PSD. So let's assume that we have a random process, continuous random process, and this random process is a wide sense stationary, okay, where the mean is mx and the autocorrelation is r in terms of tau. طبعا احنا حكينا for the random process to be wide sense stationary, the mean will have to be constant, and also the autocorrelation will have to be in terms of tau, okay, independent of time. We did that last lecture, okay? We talked about that in the last two lectures, actually, okay? Then the power spectral density can be found by using this equation, and we're going to refer to it as SXX of f, which is the frequency in hertz, okay, which is the Fourier transform of the autocorrelation, as you can see here. Okay, we all know how to do the autocorrelation, nothing new to us here. So that's basically how we found the power spectrum density. By if we already know the autocorrelation, okay, we just find the Fourier transform for it, and that will be the power spectrum density. Okay. Here are some books they introduce this one in terms of omega. But just as a reference, omega is equal to pi f, okay? So it doesn't matter to us, either f or omega will give us the same answer, okay? Now here we have some properties of the PSD. Quickly, the first one, the PSD is always larger or equal to 0 for all f, all frequencies. And also it's an even function, as you can see here, and it's real valued function. Okay. Now, if you already have the power spectral density PSD, and you are interested to find the autocorrelation, all you have to do is just find the inverse Fourier transform. Okay, as shown here in equation 2 and equation 3. In addition to that, we can find the average power of x of t. طبعا احنا حكينا average power normally it's the expected value of x of t squared, يعني two random processes multiplied by each other, okay? And this one, we showed that before, it's equal to the autocorrelation where tau is equal 0. And so you can do it directly by setting tau to 0 if you already have the autocorrelation. But if you didn't have it, it's going to be equal to this function right here, which is the power spectral density, and you take the integration of this from minus infinity to infinity. طبعا منين اجت هذه? You can go back here, right here, okay, and you just set it to, well, sorry, here, equation 2, and you set tau to 0. Of course, this one will become 1, and you will end up with this equation. So now we introduce the PSD, okay, the power spectrum density, and also the average power. We can find the average power directly from the autocorrelation or from the power spectral density by taking the integration, okay? Now, if we assume that we have x of t and y of t, they are jointly wide-sense stationary, which means that each one of them is wide-sense stationary, okay, random processes, okay, then the cross power spectral density, okay, between these two random processes is given by this equation, which is the same thing, okay, as this one. This one is for 2, but this one here for where you have two different random processes, x of t and y of t, okay? And let's say just take a quick example here. Let's see. Okay, if you remember this example from previous lectures, x of t, which is the random process, a cosine omega naught t plus theta, a and omega naught, we said they are constant, and theta here is the random process, and it's uniformly distributed over 0 to 2 pi. And if you go back to this example in previous, maybe I think last lecture we did that, okay? We did show that this function or this random process is a wide-sense stationary, where the mean is constant and happen to be 0. And also we did find the autocorrelation, and it was a squared divided by 2 sorry, cosine omega naught tau. Okay, so these are the results that we found from previous lecture, and you know how to do that. If you forgot that, you can go back to last lecture or maybe the lecture before, and you can double check on this and see how we found this. Okay. Now, what we need to find the power spectral density. Okay, and as we learn here, okay, from this equation, all we have to do just do the integration or the Fourier transform of this one here. Of course, as shown in equation 8. Now, this one is not easy to deal with, so in this case, you have to use table of integrals to be able to find the results. Okay. And obviously the results will be, this is equation 9. So this is the power spectral density, and this is of course the impulse function or delta. Okay. Now, sometimes maybe the answer here is not cosine. Maybe it's exponential. If it's an exponential, then you didn't need table of integrals. You can do it quickly. Okay. Or if it's cosine by itself, okay, well, not cosine by itself, if it's exponential, or maybe if it's a function like x or x squared, you can do some integration by parts. So, of course, if you already have the table of integrals, that will make it easier for you. But if you didn't have it, okay, and you have an exam, at the university, you can do it without the table of integrals. But this one here is not easy to deal with. I mean, you can do it, but it's going to take a long time, so we just refer to the tables. And the average power, of course, now we did find the power spectral density. Now, if we need to find the average power, as we said before, you take the autocorrelation and set it to 0. Okay. So since you already have the autocorrelation here in equation 7, all you have to do, set it to 0. So cosine 0 is equal 1. So this is the result. Or you can do it through the integration. Since you already have this one here in equation 7, the power spectral density, all you have to do, just take the integration for this one. So if you do the integration for this part here is equal to, and a squared divided by 4 times 2 will be a squared divided by 2. Okay, so it's the same results. So that's all we need to learn from chapter 7. Nothing, we're not going to go through more details. لأنه we have too many things. يعني we did cover a lot of stuff in this semester. بس احنا بنحب انه our students when they finish this semester to understand at least introduction to these topics, power spectrum density and average power and things like that. And we have another topic in chapter 8. Of course, in advanced courses, maybe you're gonna repeat this information and maybe expand on it, okay? Any questions about this topic, about chapter 7? Okay. Let's begin with the other topic from chapter 8, responsive linear system to random signals, okay? Okay, let's consider this system here in figure 1, where we have the input to the system is a random process, and we have this this impulse response or the filter. So the input x of t going through this filter, and the output is y of t. And of course, since x of t is a random process, obviously the output will be random process. So as you can see here in equation 1, this is just like a transformation for the x of t. We transform x of t to y of t, and using this equation right here. Okay, so we're going to assume that x of t is a y-sin stationary random process. It's random here. Okay, with autocorrelation rxx of tau. And like I just said, you know, the x of t is the input to the filter, and y of t is the output. Okay, in this case, since you know since the input is a y-sin stationary, we would call this system linear time invariant, LTI system, okay, because it's not going to change with time. Now we need to find the mean, the average for the output of this system. And how we're going to find it? We just take the convolution between h of t, which is the impulse response right here, or the filter, with the input. So you just take the convolution between this one and this one. And I think you did see that in EE 260, signals and systems. I remember something like that. I think you take something like, you know, you take this topic. But anyway, so this is the convolution. We did talk about convolution before. So as shown in equation 2, this is how you, you know, how we do find the convolution for this system right here. So obviously the mean here is going to be the expected value of both sides, expected value of y of t. It's going to be the expected value of this equation, for example, right here, okay? Or here, doesn't matter, either one is okay. So if we take the expected value of this one here, now this one here is a constant, okay? This one here is a constant. Okay, so you would end up with this h of tau. Now h of tau here, the integration of the impulse function or the impulse response, where t is tau, is equal the transfer function of the system, where tau is 0. Now in equation 6, I'm showing you how we find the transfer function. The transfer function, which is the Fourier transform of h of t, okay, as you can see here. So if you need to find the transfer function, you just take the integration, the Fourier transform of h of t, okay. Now this one right here, it's the same as this one except for tau, or for f, sorry, for f is equal 0. For f is equal 0. So when f is equal 0, the exponential here is going to go to 0, going to go to 1, sorry. So you'll end up with this integration, which means that the transfer function for f is equal 0 is right here. So which means the mean for this system, for the output y of t, is equal to the mean of the input, which is x, x of t, the mean of x of t, times the transfer function for f is equal 0. Okay. Now the autocorrelation of the output y of t is given by equation 7, okay, which is y of t times y of t tau t plus tau, okay. And how are we going to find this one? We just take the convolution of the filter with the input, with the autocorrelation of the input, and times the convolution of h of minus tau. Okay. Now we take the Fourier transform for both sides. واللي هي equation 9 يعني. Okay. After you take the convolution here, so you will take the integration of this one by itself times the integration of this one and times the integration of this one. Okay, that's how you do it, and the end result going to be sorry, the integration of this one, this one, this one, and the end result going to be equation 10. Okay, because the Fourier transform for this one, is really h of minus f, and h of minus f is equal to the conjugate of h of f. Okay, h minus f of h of f are conjugate. It's this is their conjugate. So we replace. So this is the Fourier transform of h of tau is right here, which is the transfer function. Okay, and this is obviously when you take the Fourier transform of the autocorrelation of x, it's going to be the power spectrum density. And when you take the Fourier transform for this one, it's going to be the Fourier transform of minus f. But like I said, the relationship, we can take this minus f and change it to the conjugate of the Fourier transform of f. These are equal. Okay. And of course, this one here, now we can multiply this one by this one. And what we did here, if this one, let's say, if this Fourier transform, not Fourier transform, the transfer function here has j, so it means this one has minus j, or vice versa. So j times minus j will be equal to 1. So we cancel the j's from both sides and multiply h of f times h of f. So we take just the absolute value squared. So again, so when we say that, we have this is a conjugate, it means which is the reverse of j. So the reverse of the imaginary part, the imaginary operator. So if this one has j in its function, this one will have minus j. So when multiplying by each other, they will cancel each other because minus j times j is going to be equal to 1, right? So the end result will be this one here, okay? And this is the power spectral density of LT system. So the power spectral density, this is the main result we are looking for, which is the transfer system squared times the power spectral density of the input. Okay, that's all we need to cover in chapter 8. We're not going to go through a lot of details. لأنه مثل ما حكينا we cover a lot of stuff in this semester, so there's no need to go beyond this. Okay, so like I said, let's just repeat what we covered today. We talked about the power spectral density in chapter 7. And we find the power spectral density, and we find the autocorrelation from the power spectral density by taking the inverse Fourier transform. And we also found the average power. And this is just an example. And here, in chapter 8, we introduced this LTI system. And the reason why we call it LTI, because the input is a random process, and it's Y-sense stationary, so the time has no impact to it. It's not going to change with time. And then we did find the mean by taking the input, the correlation between the input and the filter H of T. Okay, and we did show the mean for the output. And in here we talked about the autocorrelation of Y of T, which is given in this in equation 8, and we can find the power spectral density by taking this autocorrelation in the equation 8, and you take the Fourier transform for it. So when you take the Fourier transform for this one here, so you find you do the integration for this one first, then this one, and these are the results. So equation 11 is the one we are focusing on through this analysis, which is the power spectral for LTI system. Okay. Any questions on what we talked about today?
دكتور لو سمحت.
تفضلي.
بالنسبة للآخر كويز، ما في مجال إنه تعمل لنا كمان كويز نرفع فيه علاماتنا؟
أول شيء ما في أسئلة على النوتس اللي حكينا عنه اليوم. أوكي. معناته إحنا بالنسبة لللكتشرز اليوم كان آخر لكتشر بالنسبة للمادة، ما ظل أي شيء. تقريبا غطينا مثل ما حكينا، غطينا chapter 2 3 4 5 6، وهاي غطينا يعني 2 topics very simple topics from 7 and 8. فهاي نهاية المادة. طبعا مثل ما عارفين إنه الفاينل راح يكون كأنه حددوه بآخر الشهر، فمعنا يعني about 2-3 weeks. فمعك وقت إنه الامتحان راح يكون طبعا comprehensive مثل ما بتعرفوا. اوكي. فطبعا امتحان الفاينل عليه 50 علامه، يعني كل اللي اشتغلنا عليه الميدتيرم والكويزز كله عليه 50 علامه، والفاينل عليه 50 علامه. فاذا يعني بدك ترفع علامتك او علامتك مثل ما بدكم، you have another chance during the final. بس to answer your question about quizzes، احنا عطينا 2 quizzes وما في مجال نعطي كويز ثاني. اولا مضلش وقت، ثانيا ما في داعي لانه الافرج كويس كثير. هلا بعرف ممكن واحد يقول انا ما زبطتش بدي another chance. احنا ما يعني العمليه، انا في عندي 2 يعني شعبتين، عندي تقريبا 60 طالب. في ناس زبطين كويس، وفي ناس مثلا لسبب او لاخر ما حلفوا مش الحظ. اذا كويز مثلا ما زبط كثير بالكويز مثل ما حكينا، الفاينل على الابواب بعد 3 weeks، فشدوا حالكم و you can do whatever you want. بس ما بنقدر نضل نعطي كويزز ودروب ذا لوست وتراب لانه احنا ما ضل وقت. اوكي. فاذا ما في عندكم اسئله بالنسبه يعني العلامات، اذا مثلا واحد شايف انه لازم تكون علامته اكثر لسبب او لاخر بده يقول لي ليش. طبعا مش انه والله انا لازم اجيب اعلى، بس انه مثلا انا ما غلطت، نزلتهم من امبارح مثل ما حكينا لكم، وبتوقعش انه في اي اخطاء، بس يعني ممكن الواحد يخطئ، ما في مشكله. اوكي. بس انه يعني another quiz another homework another كذا، ما ضل في مجال، فاعذروني يعني ما بقدر. اوكي. any other questions? okay. if you guys happy with يعني the grades، I mean انه يعني ما في مشكله بالجريدز، معناته او بعتمدهم اليوم او بكره ان شاء الله، وبكونوا هاي الجريدز من 50، وبضل يعني عندك 50 علامه للفاينل which is يعني مثل ما حكينا big chunk. فاذا واحد يعني علامته شويه مش بزياده وحاب يرفعها، الفاينل على الابواب، فشدوا حالكم و good luck to all of you. if you didn't have any questions،
يعطيك العافيه دكتور.
الله يعافيك. شكرا. حسب التعليمات لحد الآن قالوا اونلاين، مثل ما بتسمعوا احنا بنسمع الصحيح. بالبداية قالوا لا راح يكون بالجامعة، بس ردوا غيروا وقالوا راح يكون اونلاين. فيعني مثل ما بدهم. انا شخصيا بدي اكون معك صريح، شخصيا بحب يكون بالجامعه، لانه التحضير اونلاين متعب بشكل يعني بتعرف، لانه بدك تتدخل للسيستم وكذا، بس يعني مثل ما بدهم يعني وشو نسوي مثل غيرنا يعني. اوكي، فراح يكون ان شاء الله اونلاين حسب، الا اذا بعد اسبوع قالوا لا، فاي تغيرات بتكون مثل ما بتسمعوا انتم يعني، بس سو فار راح يكون اونلاين، وطبعا حسب السكاجول اللي نزلوه بالجامعه. شكرا جزيلا، يعطيكم الف عافيه وجود لك تو اول اوف يو، ونشوفكم ان شاء الله باذر كورسز ان شاء الله. يلا اهلين، يلا السلام عليكم.